Class, welcome back. This is a video that I'm posting on some advanced video processing techniques for emulating things like motion sensing through your webcam. The two big things that we will learn today are sensing movement through a couple of related but very different techniques. One is called background subtraction, or actually frame differencing. Background subtraction is an entirely different thing. I misspoke. Frame differencing, and the second set of techniques is optical flow. Both of these methods have their roots in a field called computer vision, which is a very broad umbrella term which tries to emulate the human visual capability through algorithms. But the couple things that we will learn are fairly specific things dealing with movement and video. So the patches I'm talking about are already up on your canvas. There's a few additional folders which I created. Um, if you go to this folder which says computer vision techniques, you will see a set of 5 patches, and we will try and run through these today. And we will start with this patch, which is called frame differencing, to start. Okay. Now, here is my frame differencing patch. High level concept first. Movement, as we see through our visual sense, is very sophisticated than can be replicated on an algorithm, much less on a max patch that is as simple as what you're seeing. You may have seen patches like this which claim to detect movement and motion. Maybe you have already played with these things, and this is the class where we will show you that you are wrong. Meaning, yes, these things are sensitive to movement sometimes. These things are sensitive to a lot of other things other than movement. So we will work with this for now, show you how to use it, but also try and show you the limitations of this class of methods. Movement. In motion capture, when I say motion capture, I just mean that big rig that you have been working with the first half of the semester, the big motion capture multi-camera system with markers. The data that you get from that system is the closest you get to true movement sensing. Meaning, when my hand moves and the marker on my hand moves, that motion is tracked in physical three-dimensional space, and the XYZ coordinates that you see are real metric measurements in millimeters that actually correspond to true lengths and distances in the real world. So that is, for the purposes of our class, gold standard true movement, if there is such a thing as true movement. Okay, there isn't any, but for our class, that system is gold standard. These methods that we will look at are not gold standard. These things are surrogates of motion sensing. In what way? So frame differencing is a very simple idea. It is, if you have a video feed of a scene like what you're seeing on the screen right now, and if nothing in the video moves, if it's a static video, and if I get out of the scene, let me do that. I'm going to pop out of the scene for a half a minute, for half a second. If nothing moves in the scene, then frame at time t and the frame at the next time instant should exactly be the same as measured in the pixels. So hold on, let me pop out. Here I pop out. Then I pop back in. So when I popped out, if you paid close attention, you would have felt that the picture was still changing just a little bit, because the picture still looks grainy even if I'm not moving. Even if this webcam is just staring at my wall and nothing else changes, the images that the webcam records are still grainy. It's because of internal sensor noise. There is nothing you can do about it. So the image at time t and the image at time t plus 1 will be close, but they will not be exact replicas of each other when you measure the pixel values. And camera technology is complicated. A lot of cameras, like the cheap webcams that are here, come with a lot of inbuilt software that compensates for dynamic ranges, that compensates for shifting lights. So as I was popping out, I was blocking this big bright patch in the back of me, which is coming from a window. So as I block it and I unblock it, you will notice that the global brightness of the picture seems to be fading, and it's dimming and brightening, it's dimming and brightening, even though it should not be doing anything. And why is my movement affecting the entire picture? It shouldn't, but that's the way webcam software works. There is a lot of inbuilt compensation for effects like this. Bright patches or very dark patches, adjusting for contrast, adjusting for dynamic ranges happens on the fly. So even as I move out, you'll see that things are changing over time. And that is counter to the big assumption in these techniques that if you move around in a scene and if you are the only one moving around in a scene, then your movement can be detected and tracked by concepts like frame differencing. What is the concept of frame differencing? Very simple. It is subtract the current frame from the previous frame. Where is all that happening? Okay, so this patch, the way you play it, if you open it up, it will not play, right? So you start with hitting the toggle. You're going to see your webcam streaming in. It's a sub patch. Prep the video. This is something that David Tenapel wrote for me a long time ago. Prep the video converts RGB to grayscale, and it's looking at change detection per pixel. So when read up the reference for the change, jit.change, it's comparing the current pixel with a few pixels in the past and doing it everywhere. And now calculate the difference is very much implemented the same way, the way we implemented speed computations in motion capture, which is through those cross-wired connections, right? So if you open up this subpatch, look at this. T, trigger object, and two L's, lists. So it's going to create two outputs. One is a delayed version of the other. So this output is the current frame, this output is the previous frame, and then you cross them over. Exactly the same as our motion capture speed computation patches. And then you look at the difference, jit.op. So jit is it's a big library within Max, jitter, which does a lot of video processing and matrix manipulations. So you'll keep hearing this word jit again and again and again when you're doing video processing. So jit.op at op adds diff. So it's comparing the difference and then taking its absolute value, forgetting negatives and converting negatives to positives. So when you do it that way, this is the raw absolute difference. So when I move around, okay, you will see some outlines shifting, right? And typically these outlines are around the edges of objects that move. So even if I take a book and I make the book move, it's typically strong edges that show up. You can take this, and this is still grayscale in a way because you're subtracting real pixels. So the output is also, continuous value. So if you subtract 255 minus 120 something, say 125, the answer is 130. Okay, so the output is still like a grayscale picture. It can go from 0 to 200 and maybe even 255. This still is grayscale. You have the option of thresholding this. So meaning choose a threshold and jet, even though I said video goes from 0 to 255 integer, jet interprets that range as 0 to 1. So 0 is 0, 255 is 1, and every other value is fractional appropriately. So if you threshold it at 0.2, only certain significant pixels show up, significantly moving pixels or significantly strong edges that are moving show up. So here is an experiment. I shake my laptop. Okay, this is me not moving, but my laptop moving. So what is it picking up? It's picking up everything that is a strong edge in the scene. It's not only picking up me. If the table vibrates, okay, I'm just walking on my table, the table vibrates, that much of a vibration is enough for it to start picking up things in the background. So be aware of these things. Then, okay, a few other processing things. There is jit.slide. Jit.slide is very much the same way slide works in motion capture, meaning it's a temporal smoothing filter. It takes a few past inputs and averages them, so you get rid of some noise that way. And jit.slide, just like slide, the standard answers are 10 and 10. Okay, so this output will look a little, as you can see, this is like an average. It has a ghosting effect. It's averaging the past 10 frames, roughly, when I say 10, 10. Sometimes this is useful, having this ghosting effect. Sometimes it's not useful. So for the purposes of this exercise, let's not do the ghosting effect. Let's say no slide, do nothing. So it's almost like instantaneous movement shows up. There is no ghosting happening. And then jit.3m is a nice nifty little patch object which lets you compute three statistics: the mean, median, and the maximum value of a matrix. So that's the min. Min is the minimum, and then the mean, and then, okay, the maximum, not the median. Okay, so the minimum, the mean, and the maximum. So this is usually a good way to summarize everything happening in this picture into one nice nifty number. How? So I am tapping into the mean value, which is the average of everything happening in this picture, as a measure of my gross movement. This patch will not allow me to compute fine movement. I cannot say compute the speed of my wrist. That is not the capability this patch affords. This patch is about overall movement, gross movement. So you can visualize gross movement this way, but now if you want a nice measure saying, just tell me, is this movement more than this movement? Then one of the ways we can do that is by computing a mean of this image. And the more the pixels that are active, the more the movement is. And the fewer pixels that are active, the smaller the movement is, or the finer the movement is. And that is this number. So we are computing the mean value, doing some simple normalization, scaling it to some number between 50 to 1500 so we can hear it. So all of these are scaling tricks. So when I do a lot of movement, the number is big. When I'm moving slowly, the number is small. That's how this whole patch is set up. Very quick and easy way to measure movement, gross movement. Before we proceed, we will see a few downsides to this, which we have already hinted, which is my vibrations of the surface where this is placed can cause it to pick up movement. Scale is a problem. By scale, I mean the distance to the camera. Now, this is measuring movement on this two-dimensional plane, which is a picture. So when I'm closer to the camera, even small movement will get reported as very large movement because my hand is bigger and there's more active pixels. Even though I'm moving the same way, when I move further away, the movement is reported as smaller. But when I get closer up, the movement is reported as bigger because my scale is increasing as far as the picture is concerned. So these are not traits of true motion sensing. These are traits of some surrogate motion sensing. So you have to understand all the limitations before you start devising a protocol of how you would interact with the system that works off of this. Lighting is a problem. Let's demonstrate it. It's pretty bright at this point, but let's see what I can do. So I have a little table lamp here, which I'm going to pull up closer. Okay, here is my table lamp. You can't quite see it, but there it is. So I'm going to push this away so you don't actually see the light, okay, on the video. But I'm going to turn it on and off. Okay, let's see what happens. I'm not trying to move. I'm trying to stay very, very still, but I'm going to turn this on and off. Observe the movements reported. So even though I'm just turning the light on and off, there is some fine movement being reported. This is because the instant the light turns on or the instant the light turns off, when you compare that frame where the light turned on with just the previous frame, some things have changed in the pixel values, and that is subtracted and reported as movement, even though it's not really movement. To make it a little more obvious, I'm going to pull off this lampshade. Let's see if this helps. And this is this is already brightly lit, so the effect of this one lamp is not much, but we shall see. Okay, there. Saw that? Every time the light turns on and off, a big chunk of my face gets active as if it's moving, but it's not really moving. That's a big limitation of this class of methods. And anytime you deploy motion sensing in a dark room, which is the kind of stuff a lot of people do in A&E, suddenly somebody opens a door and walks in, and all of a sudden the nice beautiful sounds you're hearing will go boom 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 boom. They'll go all over the place because many of those things are actually working off of background subtraction and frame differencing like this, which are very sensitive to changes in lighting conditions. So let me show you that again. And before I show you that again, okay, let's hear it out. We will also connect the output that's coming out of these patches to some of our sonification engines, which we did in one of the previous videos. Complete the loop and see how things sound. Okay, so in this patch, I have a very simple way to sonify it, connecting this to a sinusoid, plain and simple. Connecting what to a sinusoid? I'm connecting the average activation value from this picture and also smoothing it once again. Additional smoothing never hurts. If you don't smooth things, you'll just have slightly choppy sounds. So I have a slide here, which is already an average, and then another slide here, which is a second average. And let me play this. Oh, I have that other thing connected. Hold on. I have this other thing playing at the same time. So don't do this. Yeah, do not play this, but play just this. All right, so when I move, I hope you can hear it. When I move fast. So to make a big noise, I don't have to move fast. All I have to do is to get closer to the camera. And as I said, this is the way the system works. So the more you know about how these things work, the more you can game it. The further away I am and I try to move, the more I have to move to make any noise because I'm just looking so tiny to the camera. And of course, light can also make it go up, but here it's not so much, but maybe if I get it closer to me. Ooh, let's see if this works. Look at that. So I don't even know what to call this. Okay. Light sensitive, motion sensitive, distance sensitive. This is sensitive to everything. So frame differencing is a quick, easy surrogate of working with movement. And just to show that everything you have learned in the previous classes, there is a dovetailing that's possible. I'm going to connect this up to our amplitude modulation sonification patches, and which means I'm going to disable these. Oops, I have deleted it. That's fine. So I wrote this little object, which is S. S is for send, so I can communicate between patches. So you don't have to copy paste everything into one big patch. This signal that's flowing in, I'm saying send with a variable named motion, and in my amplitude modulation patch, I receive it, R motion. It's already streaming in here. And when I plug and play this, so I turn this metro on. So now when I move, So this is doing that enveloping, right? So let's see how light works here. A game of light and sound. All right, so this is frame differencing, and this is a nice little set of techniques that you can directly work with to do some interesting movement-based visualizations and sonification. Now, these kinds of signals, in addition to, as we move along, we will introduce more patches for video processing, which when layered with these methods can open up a wide array of things. The next couple of videos will be, a few other things like optical flow. Optical flow I will not introduce in this video. We'll do it in a later one. For now, this is good. So thank you so much for your attention, and hope you can play with some of these things. Thank you.